For those of you out there who write code, I've got a question for you. This can be anybody who touches their laptop and turns a combination of letters and numbers into executable software that runs magically on its own. If you wield these powerful forces, when was the last time you had to really think about the piece of hardware that you were going to use to run your program? For most of us, it doesn't come up that often. If you're developing something locally, as we like to say, you're kind of stuck with whatever your laptop has, whatever CPU or GPU and RAM you've got available. That's where your software is going to run. If you're doing web development, web and mobile app development, there might be some more options, but for mobile apps, you're kind of stuck with iOS or Android. Those hardware footprints are relatively well defined for you. And for cloud computing options, it's pretty typical that your company has already made some really specific decisions and put some boundaries around what kind of infrastructure you can use. So for most parts of computing, it doesn't come up that often. But in machine learning, interestingly, it ends up becoming a really important part of the decision-making process. What kind of infrastructure should you use for your production workloads? Production workloads basically mean when machine learning hits the real world. What kind of computer, what kind of infrastructure should you use? So today we're going to talk a little bit about the options, the giant ocean of choices that you could make, and give you a framework to use for working through the decisions you'll need to make as you're bringing your machine learning workloads out into the real world. So just a quick, simple definition. When I say infrastructure, what I mean is the computer that you're going to use to run your AI software, to run your deep neural network or your linear regression. Whatever that computer is and wherever it's located, that's your AI or ML infrastructure. There are three main filters that you can use to think about or categorize the infrastructure options available to you that are helpful for deciding kind of what computer you're going to use. So one is the kind of silicon specifically that your software is going to run on. Is it a CPU, a GPU, a TPU? We'll talk through a bunch of those options. Secondly is where is it located? Is it in a cloud server farm somewhere? Is it on your desktop? Is it over here on one of these edge devices? Where it's located ends up also having a big impact on the kind of use cases you can support. And then thirdly, how do you want to pay for it? Can you spend a lot of money up front to buy it yourself so you physically own this hardware? Or does it make sense for you to kind of rent it? All these options are at your disposal. Depending on what you're trying to do with your machine learning project, you may choose one versus the other. Finally, there's a few questions that I'd encourage you to kind of think through ahead of time before we go too deep in this video. Jot down your answers. Do you have cost limitations? Yes, obviously you've got cost limitations, but what are they? How much can you actually spend? And how can you spend that money? Can you spend it operationally, meaning you pay as you go, you spend money as you're using this infrastructure? Or can you afford to do what's called a capital expense, where you purchase this hardware once upfront and hope that you can pay it back over time? Depending on your company, depending on the budgetary system that's being used, depending on your accountant's approval, you may be able to use more OpEx or more CapEx on the situation. How rich is the software ecosystem for the hardware that you're looking at? The hardware is a hugely important part for accelerated machine learning, but it's only as useful as the software that you can take advantage of to kind of reach those high performance chips. And in a lot of cases, the best hardware option is the one that has really rich software. So it's easy for you to take your ML model, just apply it to this other piece of hardware. Is the hardware readily available? Is it easy to purchase? Is there a giant back order? Is the supply chain secure? Those things are really important to ask, especially if you have a very secure, very sensitive use case, and if scale is going to become important. You don't want to be in a situation where you invest in a bunch of hardware that you ultimately have to change course on because you just can't get it anymore. If you have an edge opportunity, an opportunity to run machine learning models on edge devices, what are the power limitations and what kinds of models are you going to run? Are you going to be doing production inference specifically, just basically asking these models to make predictions in real time? Or are you going to be doing production training? The difference in those modes will very much influence the kind of hardware that you'll want to pick. And how much data are you processing? So Jot down your answers or just come up off the top of your head what you think those might be as we talk about all the other options available to us. So let's start with hardware options. This is the CPU, the humble CPU. It is also the backbone of basically all computing today. The architecture we're looking at right here on this screen is called the von Neumann architecture, and it is probably the most ubiquitous way to cut out a bunch of silicone, a bunch of transistors on a silicone wafer, and it was developed by a guy named John von Neumann. Dr. von Neumann, Hungarian-American, he was born in Budapest, back actually in the Austro-Hungarian Empire, eventually moved to the US, got his PhD, and got a professorship at Princeton. He was hugely influential in a whole bunch of different fields: mathematics, economics, quantum computing, quantum theory, but most importantly for us, computing. And he developed this architecture. At the time, it was also called the Princeton architecture. We now call it the von Neumann architecture. And it was composed of kind of three big buckets of things. One was the memory. So that is kind of the place where we store both our program instructions as well as our data. It includes our central processing unit, which is broken into a control unit, an arithmetic logic unit, which is kind of doing the math, and then registers, which are storing intermediate variables. And then finally, all the inputs and outputs connected via a bus. This architecture turned out to be incredibly convenient because it lets you really separate the logic of what a computer is doing in a very efficient way. There's actually computing Harvard architecture that's still in some use today in certain applications, particularly with embedded systems like microcontrollers. But the von Neumann architecture, by far and away, kind of won this battle and is the default way that basically every computer we've interacted with on a personal level kind of does its job. So how does this thing work? Well, the basic idea is that underneath the hood here, we've got a bunch of cores. And this is how, over time, central processing units were able to increase their ability to do math really fast. At the end of the day, all of our programs are taking really complicated ideas and breaking them down into algebra, addition, subtraction, multiplication, and division, if you've got a really fancy CPU. And it's converting all of that software into bytes that we want to add, subtract, divide, and multiply. To do all of these calculations faster and faster, CPU designers had to start adding in a lot of fancy techniques because the von Neumann architecture, as awesome as it is, has something called the von Neumann bottleneck, which is basically that all of these instructions and all of this data ultimately still has to go through a single ALU. And that means that you can only do one thing at a time. Now, you can do that one thing at a time really, really fast, but it's still single input, single output. So what we've done as a computing world to increase the speed of these CPUs is introduce more cores. More cores mean you can do 8 things at once instead of just one thing at a time. One of the other things that we've done is created more caches, which allows you to have data stored right next to those cores and stored in a type of memory that's even faster to access than RAM, and certainly way the heck faster than a big hard drive. So with all of these incremental improvements, we've gotten the performance of CPUs up super high, which is excellent. But for machine learning, in a lot of cases, it's still not fast enough for us to be able to develop fast-performing deep neural models that run exclusively on CPUs. So if you're running a classical machine learning model, a CPU is probably still going to be an excellent choice. But if you've begun to explore the use of deep neural networks for your machine learning workloads, then there's a lot of other options available that help get around this von Neumann bottleneck. Now, all CPUs are not the same. There's an aspect about CPU design called its architecture, which ends up becoming really important. So as you're starting to look at the options at your disposal, you're going to see kind of 2 primary architectures you can pick from. One is called the x86 architecture, and one is called the ARM architecture. Now, there's a lot of other options out there. It's not just these 2. There's quite a few others, but these are the primary 2 that you'll likely run into. Now, the Intel architecture, or x86 architecture, uses what's called the complex instruction set. It means it has a lot of different instructions of things it can do. So I mentioned before, you can do addition, subtraction, multiplication, and division. You can also do all of these other fancy things that allow you to streamline and optimize your code. And some of the more advanced CPUs out there have these smart compilers that reorder your code at the machine level to take better advantage of the chip. And there's all these really complicated and interesting things you can do, and functions that do exponents and logarithmic math for you built right into the chip. So that's super cool, and you can get awesome performance benchmarks out of it, but they are very power hungry, and they can be kind of expensive. Now, there's another ARM architecture, or another architecture called ARM, which uses typically a reduced instruction set. And these are excellent if you have more of a low power scenario. So if you're working in a constrained environment, a lot of edge devices, the Raspberry Pi actually uses an ARM chip. They're excellent for these types of applications. So in a pure head-to-head speed mode, you'll often see an x86 Intel chip winning the battle, but ARM chips are awesome for low power scenarios where you still need good performance. The reason why this matters is that when you're creating your software, it's important to know you've got to compile your machine learning software differently for each of these architectures. So you can't just write the program once and it'll work everywhere. You need to do some work to take code written for an x86 chipset and get it to work for an ARM chipset and vice versa. So keep that in mind. When you make that decision, your hardware decision is creating a software decision you have to make. Now, let's talk about computer screens. Back in the day, we had to calculate the value of every pixel on the CRT, cathode ray tube screens that our big old desktops are connected to. And that was typically done with a small chip that was right next door to the CPU. And that little graphics processing unit got really good at calculating multiple values very quickly. And then the cathode ray would quickly swipe across the screen a bunch of times and bend some photons, and all of a sudden you got something you can see. You got a UI on your screen. That approach of being able to break the math down into multiple calculations at the same time turned into an entirely separate piece of hardware, at least on larger computers, called a GPU. So these GPUs were developed to do something that required parallel computing. We need to calculate the value of all of these pixels at the same time so that we can render one screen after another again and again and again. And that parallel processing, well, it turns out it's a match made in heaven for neural networks. The structure of a GPU just looks a little different from the structure of a CPU. So here we can see in this CPU example, we've got kind of 4 cores. We've got these 4 arithmetic logic units that are connected through a common control. They're able to access the same cache. And then that cache is connected to RAM. So you've got 4 things you can do. Now, those ALUs are giants, and they're super fast. So they can churn through calculations like crazy. Sort of in a linear speed test, one CPU ALU is going to be able to do a lot more calculations per second than one GPU ALU. But just look at how many there are. That GPU has a crazy number of those green boxes. Those are ALUs. And each of those segments of boxes, each of those rows, has its own set of control and cache. So it allows you to do much smaller, sort of less complicated algorithms and mathematical operations, but allow you to do a ton of them at the same time. Why is that cool? Well, most neural networks are basically just doing matrix math, but a lot of it, and they need to do that matrix math really fast. So what it allows you to do is take this idea of multiplying the value of each of these nodes within a neural network by its activation function, and then propagate all of the results back to the next set of nodes. This is how what's called forward propagation works for a neural network. When you're not in the training mode, you're just kind of putting data on one side of the matrix and pushing it through to the end. It's a bunch of addition and multiplication. That's it. That's what matrix math is. And the architecture that we've got in a GPU lets us do a bunch of simple equations really fast. So it turns out the GPUs ended up being an awesome option for developing much larger and robust deep neural networks. And you can kind of see here how this works. We're able to load up a bunch of things in parallel that would otherwise have to be done in sequence with the CPU. So this is how the GPU gets over this von Neumann bottleneck, by providing some generalizable functions that make it easier to do simple mathematical functions simultaneously. Now, there's different types of GPUs, and when you're looking at your scenarios, looking at the use cases you have, it's important to understand if you're going to be using training in production, basically doing human in the loop with online learning in production as the data comes in from your website, let's say, doing real-time training and then delivering a new model, daily, nightly, hourly. That's a different kind of mode of operations than just doing inference, where you might update and deploy a new model to your web app or your mobile app maybe once every month or two. So training GPUs tend to be giant. They're very power hungry, and I think they're actually a great fit for a capital expense, because if you can load these larger A100, V100 GPUs up with a lot of training jobs, you can actually cut the cost curve down pretty low. So I'm a big proponent of actually purchasing hardware for training, even for local prototyping, buying a nice big graphics card for the local workstation of your data science team. Whereas for inference, they have a different set of cards that tend to be a little bit less expensive, maybe a little bit less powerful, but they're able to deliver inference, which is basically just doing the forward math for a neural network pretty quickly and much more cost effectively, both in terms of power as well as just the price of these cards. So if you're looking for training, you're going to have to shell out a lot more money, versus if you're looking to do inference, those cards, those chips tend to be a little bit more expensive and a little bit less power hungry. Finally, when you're looking for something for production, don't cheap out and try and buy the consumer version. I've got some friends at NVIDIA, and they've shared horror stories of folks who've set up a whole kind of production lab using just the traditional kind of consumer-grade GPUs, and they're just not built for production use. They burn out. They don't have the kind of warranties you need to make sure that the GPU is going to keep working under insane loads, under crazy heat. So you really do need to pay the extra money to get the commercial sort of industrial grade cards if you're going to be using kind of these local workstation type GPUs for your use case. All right, so let's talk about another type of chip. The TPU is a chip developed by Google. It's called the Tensor Processing Unit, and it takes the concept that we just talked about for GPUs and brings them to another level. So a TPU provides another type of ALU that's really specific for matrix math. In fact, it has two. It's got a matrix multiplication unit and a vector processing unit. So these two, ALUs have become hyper optimized and focused specifically on the kind of math you need for calculating tensor math. Tensors are the data format that most neural networks use for processing this kind of chain of neural network matrix math. And TPUs are designed to do that exact set of functions super, super, super fast. So it's kind of taking the GPU concept, and instead of having it be generalized to whatever type of math you want to do on those little ALUs, the TPU focuses on a really specific subset. But by focusing on that subset of functions, it's able to get crazy performance for a really low power consumption footprint, which is exactly what we like to see in production. We want to get good performance and we want to manage costs. AWS also has its own custom silicon that you could take advantage of. This is called the Inferentia, and it really is focused on inference. So whereas Google's TPU provides options for both training and inference, the Inferentia, as you might guess from its name, is really designed just for inference. And because AWS is as large and massive of a company as it is, they provide great software support for letting you take the models you've trained on a lot of the most common frameworks, particularly in Python, and converting them into software that will easily run on Inferentia chips. And again, these chips are widely available within a lot of the AWS regions. So if that's the cloud provider you tend to use, you're looking for something that will scale and something that's probably pretty cost efficient, then this could be an excellent choice. Now, the last there's two more, but one of the last unique silicon types I want to talk about is called a field programmable gate array. So this is taking this concept of hyper-specialized code, hyper specialized hardware, taking it one step further, you get to design your own silicon, but you get to do it with software. So it's kind of an interesting paradigm where you're using code to define the structure of your FPGA to be specific to the software that you want to run on it. So they can be really fast. You can design them to be very low power because maybe you've got an algorithm that only needs to do like 3 functions. And you can basically design the math into the hardware. So the calculations are basically defined by the structure of the actual FPGA. And so you can program them by rerouting inputs and outputs and then connecting logic blocks together in different ways. And the other nice part is you don't have to do any soldering. So if you muck up your FPGA, you can basically reuse it for a different application, fix it if something goes wrong. It's very forgivable. But at the same time, it does take a lot of expertise and it takes a lot of time to get it set up correctly. So it's not for the faint of heart. It's not a fast option. But if particularly performance is very important in a low power context, it could be one of the best options available to you. But word of warning, they're not always easy to get access to. So just be really thoughtful about the supply chain for whatever type of FPGA you might choose, particularly if you're looking for edge applications. You don't want to be in a scenario where these devices are no longer available by the time you're ready to use them. Finally, you can build your own chip. Don't recommend it. I think it's a terrible idea. But there are certain situations where building an application-specific integrated circuit, or ASIC, is the only option. This is true in scenarios where you might be doing, in some cases, really sensitive sort of security and encryption work. There are certain situations where you just need a separate chip to do a type of encryption that's really important for kind of a larger system. This is true of a lot of Apple devices. They have separate chipsets just for security and encryption. That could be true for perhaps machine learning applications or workloads that you might have at your disposal. But boy, oh boy, is this going to be a long, expensive, arduous journey. The TPUs that we talked about, the Inferentia chips, those count as ASICs. So take advantage of the investments made by other big, scaled companies and use the hardware that they've taken advantage of, because it's going to be a long road if you try and design your own. So how do we compare all of this hardware? Well, I tried pulling together metrics and data from a number of different sources to be able to give you one chart to say, here's how fast a CPU is, here's how fast a GPU is, a TPU, an Inferentia chip, FPGA, on all these scenarios. Quite frankly, it's darn near impossible to find. I think the best option that you could find today is through an organization called MLPerf. They do performance assessments of various combinations of sort of standard machine learning models on standard data sets on a variety of different hardware footprints. That's probably the best bet at your disposal, but they don't cover every scenario. They don't cover every type of data, every model. So you may have to do some R&D yourself, because a lot of the chipset providers, they're going to show the comparison that works best and shows off their hardware the best. So NVIDIA is going to show charts where GPUs perform really well. Google is going to show charts where TPUs perform really well. ASICs are going to show scenarios where LSTMs perform really well on, what is that? Yeah, that's the FPGA. So be thoughtful, read the marketing material, follow along as best you can, but recognize that you may have a hard time finding apples and oranges comparisons. So kind of putting it all together, this is kind of an assessment of where you stand today with the choices you might choose for your machine learning applications. If you're doing general compute and classical ML, don't even think about doing anything else. Stick with the CPU. Stick with CPUs that are consistently accessible. Stick with CPUs that have good software support, and look for frameworks that let you accelerate the CPUs you already have today. In a lot of cases, you can actually get excellent performance, even on deep neural networks, if they're small enough, on a CPU. And the costs are absolutely worth the effort, because using a CPU is a much better cost. Using a CPU is far more cost effective than any of these other hardware types. Now, if you're moving into deep neural networks and simulations, This is where a GPU, a TPU, an Inferentia chip starts to become really, really advantageous, especially for larger deep neural networks. There's really no comparison between the performance that they can offer and the performance a CPU can offer. Now, is a TPU faster than a GPU? Yeah, sometimes. A GPU, I would say, is more flexible. TPU might have better performance in certain situations. The Inferentia chip, probably comparable performance to a TPU, again, situationally. They each have their role to play, but it tends to be when you're using a more sophisticated, more computationally expensive model. And then finally, FPGAs are great if you really got some customized HPC you want to do. If you tend to be in a scenario where you're going to be creating a new model on a regular basis, redesigning that model, redeploying new versions of models, daily, weekly, monthly, probably not a great option. But if you've done some research and you've developed a model that's going to be working with something, and I could invent an idea, some sort of like physics-based phenomenon that isn't likely to change some universal aspect of starlight, and you've kind of pulled that aspect out of the universe and turned it into a model, that might be a good use case for an FPGA. But if you're trying to create models to simulate human behavior or interpret human behavior, probably not a great option, because those models are going to have to change so fast. You're going to spend a lot of your time optimizing and rebuilding your FPGA. And the same would be true with custom ASIC. So be really sparing with the use of those two more custom options unless you feel like you have a solid understanding of the world and which your model is going to be performing. AI hardware continues to explode. We've talked through 6 of these options, but every day there are more and more options available to you. So keep your eyes open. Do your research as best you can, but stick to this advice. I would say start with CPUs, and then slowly move from left to right on this chart in terms of complexity, and you're going to be in a pretty good situation, and more importantly, a cost-effective situation, particularly in production. The costs are as important as the actual performance you're going to get. So, again, some questions to think about, some things to consider as we put all of this together. This is kind of my take on where and when I would choose a particular piece of hardware given the situation I was in. So on the training side, GPUs are really hard to beat. The main reason is that they're very flexible, and particularly when you're training new models, especially when you're maybe testing out different architectures, testing out neural networks versus decision trees, testing out different neural network architectures, trying to increase the size of your network, trying some of the large language models, LLMs, to do a particular task for you. GPUs are just very flexible because each of those ALUs has so many different types of calculations that they can provide. So I would say, for my money, if I'm doing training, I think GPUs are an excellent job for the flexibility they provide, or an excellent option for the flexibility they provide. And in a lot of cases, unless I'm in a research lab, I'd probably go the cloud route. I'd probably do kind of an OpEx investment where I can do quick R&D and testing exercises in the cloud for training, and then shut those instances down the second you're done with training. Now, I would say purchasing GPUs starts to become really advantageous if you're doing things on-prem. Maybe there's for security reasons, maybe for performance reasons, maybe for network access. There are some scenarios, especially if you have an R&D lab, where purchasing a GPU because you're using it so much starts to become more cost effective. I think the math I did recently was something like if you're using a GPU at somewhere around 60% utilization, it starts to become more cost effective to just buy it than to use it in the cloud. So something to keep in mind. But at the same time, TPUs do offer training support. So if you're able to take advantage of Google Cloud exclusively, it could be a really good fit for you. On the inference side of things, I again would say if you have cloud-based use cases, GPUs are an excellent option. They give you the most flexibility. You can move between clouds really easily. The software support is pretty strong. But if you know and if you're confident that you can take advantage of Google Cloud exclusively, or you can take advantage of AWS exclusively, I think the Inferentia and TPUs become much more viable. So be thoughtful, because if there's a reason why you need to provide multi-cloud support, then you're going to have to re-architect and start developing multiple pipelines for your models to run on different kinds of hardware in different environments. And that's a real can of worms. It can be done, but it's a lot more work and orchestration, and your DevOps team will thank you if you really have created a single way to deploy, package, encode, and run your models. And then finally, for edge applications, this is where some of the more custom chips become a lot more interesting. CPUs actually start to become a great option at the edge because of the power hungriness of the other exotic chips. CPUs are much more low power friendly, particularly those ARM chips. So that becomes a real good option. FPGAs and ASICs also become great options at the edge because of their footprint and their power consumption. So some resources for you if you're interested in learning more. Highly recommend Elements of Computing Systems. It's a great book. It talks a lot more about the different architectures and really how we got to this place where we are with von Neumann Architecture. There's a great blog that I referenced today with some really detailed notes on all the hardware options and a lot more I didn't cover. And then if you're interested in more detailed performance metrics about the hardware options at your disposal, definitely check out MLPerf. It's available on the ML Commons website. They've got really good metrics. And if you're doing sort of standard machine learning operations like computer vision or NLP, you're going to find some really good metrics. So highly recommend checking that out. And there's some good resources there for you. All right, last but not least, this recording is actually a little bit behind schedule. 2 of these talks have already happened. So choosing the right infrastructure for your production ML, that's this talk. Running Hugging Face models on a Raspberry Pi, that was actually already up. It's on YouTube. Check it out. It's actually a great video. My friend Brad did a tremendous job with it, and it's pretty fun to watch his Tiny Burt model running on, in fact, this Raspberry Pi right over here. But next week, we've got a talk on model serving. So highly recommend swinging by if that concept is new to you, particularly if you're a data scientist, but you don't have a lot of experience with Docker or Kubernetes, hosting, creating APIs and web services and the whole 9 yards. It's just going to be a great general overview for anyone who's kind of new to the whole model serving side of things. All right, well, that was everything. I'm Seth Clark. Thank you so much for the time. It was great to be able to spend some time digging into this. If you have comments or feedback, talk to us on Discord. Our Discord server is free and open to anybody, and we'd love to hear your thoughts on how you choose your hardware for machine learning applications. Thanks again, and have a great one.